Hello and welcome to Module 7 of this webinar series on the Rural Access Index. These webinars are part of a TRL project with the aims of refining the methodology for RAI calculation, piloting application of that new methodology, and increasing awareness and use of the RAI in general. This presentation is part of a series, and each webinar in the series is a maximum of 10 to 15 minutes long, and some frequently asked questions are included at the end of each module. The webinars will cover the topics shown here. This final presentation covers the future direction of the RAI. We do recommend that you view these webinars in the sequence presented, but all the presentations will be made available separately and can be accessed as required. So firstly, let's just recap some of the background of the RAI, and we covered this in more detail in Module 1 if you want to go back and listen to that. But essentially, the original 2006 methodology was based on household surveys. Then the World Bank report on RAI in 2016 was based on geospatial measurement of RAI, but also considered alternative methods of measurement in the future, which included remote sensing, for example, from satellite imagery. At the time, there was not sufficient evidence to trial remote sensing as a methodology, but its potential was recognized. The status review of the updated RAI by Vincent in 2018 also considered new technology and suggested the potential for using mobile phone network data to determine the all-season status of a road. This webinar considers how these technologies and others could be used to measure RAI in future. The technologies discussed in this presentation for measuring RAI in the future are largely based on existing technology that could potentially be modified to assist in RAI measurement. With some innovation, technologies used in high-income countries could be adapted for use in low- and middle-income countries. The last part of this webinar considers technologies that are not yet well developed, but nevertheless have potential to be used for RAI measurement beyond the horizon or in the long term. A free open source measurement tool has been developed to show RAI for each country in the world using open source data. This also includes the 3 in-country RAI calculations carried out by TRL as part of the ReCAP RAI project. The open source data used includes WorldPop, OpenStreetMap, and the GRUMP database, as mentioned in Webinar 4. This measurement tool is due to be presented on the UN Global Platform as a demonstration to motivate feedback and to allow countries to assess their potential for RAI measurement. The longer-term aim is for this tool to be developed so that countries can visit the site and carry out RAI measurements independently, using their own data or a mix of open source and their own data. Any calculations will still require endorsement by the responsible agencies in the country, including the NSO. So I'm now going to give you a short demonstration of this tool. Okay, so to start we want to go to this web address here, rai.azavea.com. And you can do this in any modern web browser, and you will be presented with this visualization here, which is effectively the home page of the Rural Access Index measurement tool. And the visualization shows a map of the world, which is color-coded according to RAI, with countries with the higher RAI being shown in dark blue, and countries with lower RAI in light blue. Now, the RAI figures used to generate this map have been effectively auto-generated by this tool using the 3 open data sets that we've covered previously in this series of webinars. So OpenStreetMap for the roads, WorldPop for the populations, and the GRUMP database for the urban-rural boundaries. Now you can navigate this map just as you'd expect, so you can zoom in and pan around, and as you hover over each individual country you will get the RAI score popping up as we see here. So we can also zoom into individual countries, so I'll click on Uganda here to get this more detailed view, and I'll just zoom in slightly to make sure we get the right level of detail. And what we'll see is the all-season road network you can see in white here. And around this network you can see this black or dark grey buffer zone Now this is effectively a 2 kilometre buffer zone around the roads, and of course that 2 kilometres relates to the RAI definition. And so by that definition, any population which lives within this this buffer zone is served by the rural road network, the all-season network, and the population that lives outside of that buffer zone is effectively not served by the all-season network by the RAI definition. Now you can see down here there is a color coding for the population density, so the darker areas of darker orange denote areas with higher populations. These areas here with the very pale orange are almost certainly areas where there's zero or next to zero population. So very quickly we can pan around the country and we can very quickly identify areas which are pockets of high densities of population which are not served by the rural all-season roads network. We can have a look here as well. Look, there's very high density around here. So it's a very useful tool in that respect, just to give you this simple and easy to understand visualization. And as you zoom in, you'll get more detail popping in. So these roads here were not considered to be part of the all-season road network. Now on the left here, you'll see this table with the numerical data which is relevant. So of course the actual national RAI indicator, which here for Uganda is 72%. The population figures, so here we can see just under 25.8 million rural population served by the all-season rural roads network, and the length of the roads network considered in the calculation. Now it's interesting also to look at a country where there is nationally reported information as well as this automatically generated RAI. Malawi is one such country because TRL in 2019 did the exercise to calculate the RAI for Malawi using the processes and the methodologies that we've been discussing in the previous webinars. So when there is a country which has nationally reported RAI as calculated using this methodology, what you can get in this tool is a slider which allows you to compare visually the outcomes of the calculations using the two different methodologies. So the in-country data is on the right hand side of the slider, and the let's call it the automatically generated estimate using the open source data sets on the left hand side. You can also compare the outcomes here in terms of the raw numbers, and it's interesting to note that there's only a 1% difference between the automatically estimated RAI and the RAI which was calculated by TRL using in-country data. So in conclusion, this tool is free, it's open source, it's easy to access in a web browser, and it gives you a very powerful tool for visualizing rural accessibility in any given country of the world, and we encourage you to take a look at it. There's an initiative managed by the UN Big Data Global Working Group called the UN Global Platform. This is being developed to provide tools and services for NSOs to use big data. The data on the platform includes Earth observation, mobile phone network data, and social media, and the platform will provide tools and services to use those datasets for statistical purposes. The UN Big Data Working Group website showcases some projects, including datasets such as a smart meter electricity dataset, scanner data, and credit card data. It has significant potential for all sorts of statistics and indicators. The intention is to host the RAI Measurement Tool within that global platform. Big data is defined by its volume, variety, and velocity. It's generally accepted that data is big when it cannot be processed by traditional means. Datasets are growing rapidly, partly because they are increasingly gathered by numerous and cheap information sensing devices such as mobile phones, tablets, and cameras, to name just a few. In addition, many more organizations are making data available through open source outlets, with governments and aid agencies especially adopting open source policies. Data science is described as a multidisciplinary field of science that can extract knowledge from both structured and unstructured data by using algorithms, systems, processes, and scientific methods. In terms of measuring the RAI, big data is a potential source of good information. Machine learning is a field of computer science that provides computers with the ability to learn without being explicitly programmed. There's potential for big data and machine learning to work together to provide accurate and rapid information on road networks and transport movements. So in the following section, we're going to look at technologies that are already established and available, and that with some innovation have the potential to be used to assist in RAI measurement. Earth observation technologies such as satellites can be very useful for identifying roads and then checking against the current data sources to test for completeness. There are many open sources of satellite imagery online, although the resolution and the date of acquisition does vary. The Facebook Data for Good program, for example, has produced a tool to interpret satellite data and identify roads that are likely missing from OpenStreetMap. This tool creates vector data and provides an interface where that can be verified in the field and uploaded to OSM. There are several regional data cubes, which are tools that harness latest Earth observation data and satellite technology to help countries address various issues relating to major topics such as agriculture, food security, deforestation, and of course, infrastructure. Aerial imagery and LiDAR from planes, helicopters, or drones can also be used to identify and map road networks very accurately. Research has also been carried out to assess unpaved road condition from satellite imagery, drone imagery, and other remote sensing, which has the potential to provide a summary of the all-season status of roads. Mobile phone data has tremendous potential to provide insights to transport movements. With machine learning and big data techniques, very large datasets can be analyzed to obtain detailed information on vehicle movements. This has the potential to be used to track movements on rural roads and determine the all-season status of those roads by estimating traffic volumes and speeds, which can be used at a high level to identify seasonal variations. This can be done using cell-to-cell data, and this means smartphones are not necessary, and this makes it more appropriate for rural areas where there is lower coverage of 3 and 4G. The data does, however, have to be anonymized before it can be used for such purposes, and mobile phone companies are likely to charge for its use. So the feasibility for RAI would need to be explored further. It's likely that specialist expertise would be needed to analyze the data. There will also be increased capacity to use smartphones and GPS for more accurate data in the near future as the cell coverage and ownership of smartphones increases. Useful information could also be extracted from social media to assist in the measurement of RAI. If people could be encouraged to report issues with rural roads, especially closures in the wet season, this data could be collated and used to estimate the all-season status of road networks. There are several apps where users are encouraged to report issues. For example, Fix My Street in the UK, where members of the public can report issues directly on the app, from potholes to faulty traffic lights. The app provider then passes this data on to the relevant council. The user can take a photograph and the location is georeferenced via a tag. The app also reports when the issue has been resolved. Data scraping is a technique whereby human-readable data is extracted from a machine source, which could be a mobile phone, social media, a computer, a report, online mapping. The World Bank IE Connect program is scraping social media to produce real-time georeferenced crash maps of Nairobi to monitor road traffic incidents. This generates high-frequency data on crashes and crash density around urban hotspots, using a real-time verification process to record characteristics related to the crash. There are potentially useful sources such as Google mobility data, which show variation in mobility at different location groups on a daily basis. These data are collected automatically and can be used for many different types of analysis and at different granularities. The example shown here was taken during the COVID-19 pandemic, and such reports could in theory be used for other applications, such as identifying reductions in accessibility due to flooding. The Internet of Things is a network of physical devices, vehicles, buildings, and other items that are embedded with electronics, sensors, software, and connectivity to the Internet or other networks that enable these objects to collect and exchange data. In future, sensors in vehicles traveling on rural networks could allow agencies to gauge traffic volumes and speeds on roads. We're now going to look at new or emerging technologies and applications that may have potential to be used to contribute to big data and to be used for monitoring indicators such as the RAI. There are now ways to measure air pollution remotely using satellites. Fossil fuel-powered vehicles create pollution when they use a road, and in many low and middle-income countries, vehicles create high levels of this pollution due to their age and lack of maintenance. There may come a time when vehicle movements can be tracked by monitoring the pollution they leave behind. Synthetic aperture radar is an active mode of satellite monitoring, whereby radar waves are dispatched from a satellite and their return is monitored by a sensor. This creates a point cloud that can provide information on materials and terrain. As radar is sensitive to the physical structure of the surface, it could be possible to determine pavement characteristics such as roughness or incidences of flooding. Hyperspectral monitoring is a remote sensing method that can help to identify different Earth features or materials by analyzing their spectral reflectance patterns or spectral signatures. Each material has a unique spectral signature, as can be seen in the graph to the right, where the signatures are visualized in spectral reflectance curves as a function of wavelength. Hyperspectral monitoring goes one step further by using a higher spectral resolution with wider land coverage. This allows features beyond the visible and NIR range to be detectable. If the resolution can be improved enough to identify road surfaces, this has potential for RAI monitoring. And similarly, it could be used to identify areas of flooding. Solar-powered unmanned aircraft have been developed to fly in the stratosphere. They run exclusively on solar power and fly above the weather and conventional air traffic at 70,000 feet. They are called high-altitude pseudo-satellites and are able to stay airborne for months at a time. This particular pseudo-satellite we can see here was developed by Airbus, but others are also being developed. These aircraft can host various equipment including high-resolution cameras, video, LiDAR, and even provide broadband. The potential of these pseudo-satellites to monitor roads and transport movements is obvious, but the feasibility will depend largely on cost and availability. All of the technologies will provide additional data at higher resolution and will have potential to be used to calculate indicators in future. This module has been the last in the series of 7 modules on the Rural Access Index. All other modules are available on the ReCAP YouTube channel and on the World Bank Data Catalog website. So we're now going to go over some frequently asked questions relating to the topics we just covered in this webinar. So the first question is, how will low and middle income countries get access to AI tools? Well, the UN Global Platform that we mentioned is one possibility. We also mentioned the regional data cubes, which will start to make these tools accessible to governments and statistical offices in low and middle income countries. It's also worth noting that many AI tools are open source. Question 2. How could we use Google mobility reports to calculate RAI? One possible way is that big data analytics could identify significant drop-offs in mobility at certain times of year in certain places, which could be an indication that some roads are not all season. This would need further research before it could be proven to be reliable. Question 3. Beyond technological factors, do you anticipate changes to the methodology of RAI calculation? So there will not be changes in the methodology for calculation of the RAI before 2025, which is the next official opportunity to change or add SDG indicators. However, we do see the potential for a secondary indicator for intermediate means of transport such as motorcycles and navigable waterways, which also provide important access to a large number of people around the world. So that's the end of this webinar. Thanks for watching, and we hope you found it useful. You can find more information on the ReCAP website and in the references provided earlier in this presentation. You can also access the other modules in this series via the ReCAP YouTube channel and on the World Bank Data Catalog website.